All right. So today we're going to talk about chapter 11.6 ratio group test. Plan anyway. And I'm happy to answer any questions about anything else before I get started here. I'll point out that when I've got the exam scheduled for this, the first exam, just so it's on your horizon. I have exam 1 penciled in right now for, I believe, February 4th, Friday. Okay. Just keep that on your radar. Exam 1 will cover all of chapter 11. Okay. And so my dates, when I schedule these things, unless they'll never come earlier, it's possible they may get pushed back. I don't see needing to push this back. Okay. But almost certainly, I mean, I never move exams early. So there will be no earlier than that. Just make sure that you're ready for an exam on February 4th. Okay. So last time, or 2 times ago, I talked about something called the rearrangement theorem. I want to contextualize now the tests that we're going to be doing. Actually, are there questions about anything before I start? Okay, so I talked about something called the rearrangement theorem. The idea that if a series converged because it was an alternating series, but then you took the absolute value and it fell apart, that it could add up to any number. So I'm going to remind you that difference, and then we're going to talk about names for those types of convergence. And the very first thing I want to do is I want to point out that an example of how this works, like why this happens. So the big idea, the reason that we need tests, the idea is that we want tests for convergence that is better than alternating series convergence. Because alternating series convergence is kind of terrible by itself. So if you have a series with A1 minus A2 plus A3 minus A4 converges, but A1 plus A2 plus A3 plus A4 and so on diverges. And remember what I pointed out, that this could be rearranged to equal any number. Rearrangements of this will not add up to the original thing. I'm going to do an example of that. To show you the kind of like cheesy algebra that you can do to break this thing. If this converges, but that diverges, then A1 minus A2 plus A3 minus A4 and so on can be arranged to add to any number. So it's not a really strong type of convergence. So this is going to be the justification for tests that look at alternating series, but then beat them up to look at the positive terms. Okay, so here's an example of like how this breaks down. So this series this sort of alternating harmonic series has a limit that's actually pretty easy to write down. This equals log 2. When you arrange it that way. Now, I will point out that if you took that series and you multiplied it by a half, that should be something we can do, right? I mean, it's arithmetic. If I have this this particular series right here, and I multiplied the whole thing by 1/2. You can think about this in terms of the partial sums. This is totally okay as long as the limit continues to exist. Well, on the one hand, this will be 1/2 of the natural log of 2, right? I mean, multiplying one side of the equation by a number, it's going to be the same as multiplying the other side. And if I actually distribute this inside, I get this. It's arithmetic, right? I took this alternating series. I have multiplied it by a half, and I've gotten a new expression, very trivial looking expression for 1/2 of the natural log of 2. So now I'm going to do a ridiculous manipulation. I'm going to take this series and I'm going to spread the terms out a little bit. So if I have a series like this, it's okay to put zeros in between all the terms, right? That's a legal move. I could put zeros in there if I feel like it. So imagine then that I just take that series and I say, well, whatever it's equal to, it also is, this series will also be equal to 0 plus a half, and then remember plus 0 minus a fourth plus 0 plus a sixth. Now, have I changed that series by putting zeros in between the terms? I mean, should it add anything different? Well, no, I just put zeros in there, right? I've added nothing. I added a whole bunch of zeros. Nothing should have changed. This is still equal to 1/2 of the natural log of 2. But now notice that if I take this series, I can add it to this one by doing this. 1 minus a half. I'm going to subtract or add here. Add the series by doing, which terms do we scoot in here? Do we even need the first 0? Yeah. 1. So I'm double checking what the order of addition is here. By this series, I did this right before I came to class, and now I don't totally believe what I just did. You add these up. You have one that's arranged term by term. You have a different one that's arranged term by term. And when you do that, well, let's see, 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, and so on, which that was equal to log 2, right? This is the original series again. So if you add, what do you get? I mean, I can add these are numbers, I can add them. These are numbers and I can add them. And when you add series, you add them term by term, right? First and first, second and second, third and third, fourth and fourth, and so on. What you get when you add this is, let's see, 1, that's a 0. 0 plus a third is a third. A quarter minus a quarter is minus a half. 0 plus a fifth is positive 1/5. There's a 0 from the sixth, minus a sixth. That plus that is just 3/2 of a log 2. Yeah. So I haven't done anything here. I just took this series, multiplied it by a half, split some zeros in here, and now I'm adding down term by term. But notice that this looks like this. Minus 4, I think is what I'm saying. You add this up, what you end up with is a rearrangement of this series. Every term that's here is in this sum. We did 1 1/3 first, and then the minus a half, and then a fifth and a seventh, and then the minus 1/4. But this list of numbers is the same as this list of numbers, just rearranged. I mean, I can take zeros out. I can change the answer by deleting zeros, right? So this has every number that's in that list. But notice, because they appeared in a different order, I have started with this list of numbers and said it added up to log 2, and then rearranged it so it adds up to also 3/2 log 2, just by flipping some of the terms around. This is not something that you want to have as a property of lists of numbers, right? You don't want it to be the case that, like, I'll say, well, I'll just do 2 of the positive terms and then 1 of the negative, and then 2 more of the positive and then 1 of the negative, and then 2 more of the positive, 1 of the negative. That shouldn't change the answer. This list is the same list of numbers, but it adds to a different quantity in the end. Okay. So this type of convergence, this only happens because this thing converges, but the positive version of it does not. This property of being able to manipulate these things so that they add up to different numbers by writing them in different order. That has to do with the fact that this happens because the sum of 1 over n diverges. The positive series diverges, even though the alternating series converges. So we're going to name this type of convergence. We named it last time. If you have divergence in the positive terms, but convergence in the alternating series, you call that conditional convergence. Conditional convergence, we talked about last time, is kind of terrible. In fact, you should probably not even believe me that this makes any sense at all. I just showed you that two things added up to two different numbers, even though they're the same thing. You shouldn't believe it. It's an artifact of the way we define convergence of series. Okay? So we're going to exclude, in a lot of cases when we're working with these things in the real world, we don't want this. We want to stay away from places where this kind of behavior is possible. So we're going to name it, and then we're going to work around it. So if this sum converges, and this sum diverges, we're assuming here that the ANs are positive numbers, right? So in the background, you should think AN is positive. Then this sum is said to converge conditionally. The reason that we use the word conditional here is because, well, it diverged. Its convergence is conditioned on the fact that we made it alternate, which is kind of we introduced this artificial behavior onto it. So conditional convergence says it only converges in the alternating form, not the positive form. If, on the other hand, you have, well, if on the other hand you have this, if AN converges, if the absolute value of the ANs converge, in fact, we should just write this. If the absolute value of the ANs converge, then minus 1 to the n AN converges, then it's automatically the case that this converges. So if you converge when you're positive, you automatically converge when you alternate. Converging while you're positive forces you to converge when you alternate. So this is called absolute convergence, in reference to the absolute value here. So to make this clear, this series converges by the alternating series test, but the sum of the absolute values of it diverges. So we say this is conditionally convergent. Conditional convergence means we apply an absolute value and we get something divergent out the other side. Okay? And then we have all the rearrangement theorem breaks down. Arithmetic stops working. On the other hand, something like this that converges by the alternating series test. Alternates? What does the alternating series test say you need? To converge, what do you need? Hold on, all I hear is like somebody yelling over here. Right? Loud up there. Okay, what did we do?
The limit of n approaches infinity of like.
Okay, does that work? Does this go to 0 and goes to infinity? Cool. Does it alternate? Yeah, right. Is it decreasing? Let's see. F of x is 1 over x squared. F prime of x is minus 2 over x. So the minus to the third. Well, this is positive when x is positive. That's a negative sign, so it's always negative. So it is decreasing. So this converges by the alternating series test. But it's also the case we could have not seen that immediately, because as soon as I take the absolute value, that converges because it's a p series. This is a convergent p series. So I didn't actually even need to check this converge. As soon as I knew this was true, that also has to be true. So this is why we talk about absolute convergence. Absolute convergence contains alternating convergence. So we say this sum converges absolutely. The nice thing about absolutely convergent series is you can arrange them any way you want and they always add up to the same number. So absolutely convergent series act exactly the way numbers should act. The limit theorems all work. You can add them to each other and it's okay. You can subtract them and it's okay. That is not true for alternating series. They're not arithmetically stable. So when you're looking at a series, you want to test for convergence, then so I guess the first thing here is notice that this definition only applies to series that have terms that aren't positive. If you have positive terms, you just talk about convergence. So if the series has positive terms, it's just convergent or divergent. You only have to talk about absolute convergence when you have series that flop around like this. Make sense? Okay. So they go through the process of proving this. We don't need to do that. But let's look at, say, this series. Okay. First off, does the alternating series test even apply to this? I mean, are the go ahead. Is that
Yeah, probably.
why?
Cosine keeps switching between. Oh, there's no pi number.
There's no pi, right? This is just spitting out random numbers between -1 and 1. They're not negative ones and positive ones. They're all over the place, right? Cosine of 2 is some radiant. It's a measurement of some radiant thing. So -1 and 1 aren't coming out of this. Big, huge, irrational decimals are coming out. So I can't even use the alternating series test on this because it doesn't go plus, minus, plus, minus, plus, minus. But maybe it converges anyway because I can take the absolute value and show that the absolute value converges. So what about this one? I can't apply the alternating series test because it doesn't go -1 plus 1 minus 1 plus 1. So let's look at the absolute value of it though. What can you tell? So we've seen this trick in here already. What can you tell me about cosine of n inside of an absolute value sign? What do I know about this? Between 0 and 1, right? Cosine of n is a bounded function. It's bigger than 0, less than 1. Now, of course, you're never going to hit equality if you're putting integers in, but that's a bound, right? Cosine of n in absolute value is less than 1. And bigger than 0, it's absolute value. So that means that whatever this series does, I guess I can write it like this. I know that this is true. So what does that tell me a useful series? What do you think this series should do? Why?
It's like a P series.
Looks like a P series would be equal to, right? When I look at this, I think, okay, this is less than 1, and on the bottom it looks like n squared. Whatever this is doing, it's flopping around, but this thing is headed to 0 like n squared. So I'm going to use just the comparison test. Reasonable? Because cosine is bounded above by 1. This term must be less than or equal to that one. This converges. This forms a convergent P series. So by comparison, this must. This converges by comparison with 1 over n squared. The terms of this series are smaller than terms of that one. That series converges, therefore, so does this one. Okay? What do we conclude then? This is great, except this doesn't answer our original question was, does that series converge? This answered the question of, does this series converge? What does that say about that one? So there's only 3 possible answers: divergent, conditionally convergent, or absolutely convergent. What do you think? Why? Yeah, I mean, absolute convergence is, the definition of absolute convergence is, if the absolute values converge, it forces this to also converge. So you would say this sum converges absolutely, or is absolutely convergent, whatever structure you like with your mathematical language. But the idea is, we tested this series by looking at the behavior of its absolute values. And notice we had to blend multiple techniques together here, right? We had to use the comparison test in P series to get somewhere, to get like a starting point. Okay, so this is typical of dealing with series that have non-positive terms. All right, so a more general approach shows up is, what do you do series containing factorials? Remember, we've got these flags that tell us when we're supposed to use certain tests, right? So one of the tests we had was that if you have exponential type things, you're supposed to use the geometric series argument. And another one was if you saw polynomials, you probably were going to use the integral test in some form, right? Or the comparison tests. The question is, what do you do with series that contain like factorials in them? Because these tend to be the sort of series that you consider when you're doing this. So for example, here's a good one. Better of this. A lot of factorials running around inside there. It's not obvious to me that you can hit this thing with a limit comparison test, or that you can hit it because it doesn't cancel in an easy way necessarily. So when you have a series containing factorials, and many of our series will contain factorials, we need a tool. What we really want is a tool that we can use to attack series that contain factorials. And that's what the content of the ratio test is going to do. The ratio test is much more powerful than just dealing with factorials, but it allows us to treat series containing factorials in a very straightforward way. So, ratio test. The ratio test is a test for absolute convergence. What it says is, I will follow here precisely. Oh, there's lots of parts here. If limit as n goes to infinity of the absolute value of the ratio between an plus 1 and an, if that limit is L less than 1, strictly less than 1, strictly less, then this series is absolutely convergent. And notice here, I mean, what is the difference between this and the comparison test? This is still, we're testing a limit here. What's the difference between this and a limit test? Like a limit comparison test. One small difference and one really big one.
The limit comparison test, it's to get like, one further of the original.
Yeah, what were you going to say?
Absolute value.
Okay, so one is that it takes the absolute value, which means it destroys any negative behavior. And two, what you're saying is exactly correct, right? The idea here is I don't have to compare this to anything. There's no choice to make here. This is just a computation. There's no comparison to be made. I'm comparing the series to itself. Right? If you want to know what's going on in this limit, what I'm measuring is as the series gets further on, is the ratio between the terms less than 1, means are the terms shrinking fast enough to converge? Okay. Essentially, if you want to look at it, I'm not going to prove this, but the proof of this works because essentially what you're doing is comparing this to a geometric series. That's really what, as soon as you say it's less than 1, there's some number that you can compare these to. And then there's a geometric series comparison running around the background. So the comparison test is actually used to prove this theorem. So that's part 1. So we can actually use it. We'll use part 1. Well, let me finish it first before I start applying it. Okay, so part 2 of the same theorem says if the limit as n goes to infinity of an plus 1 over an is equal to an L that's bigger than 1, or it is equal to infinity, then the sum not of the we don't somehow recover conditional convergence here. So we get a statement here about conditional convergence. If it happens to be the case that this particular sum has the limit L bigger than 1 or infinity, then this just diverges. So it's unambiguous in that case. This is basically saying that the ANs are somehow getting bigger as n goes to infinity. So this is kind of including the test for divergence in here. If, finally part 3, if the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to 1, then you don't know anything. Test is inconclusive. You have no idea. Could diverge, could converge, doesn't say anything. Okay, so the problem is, I mean, the ratio test is amazingly powerful. The problem is that there's a lot of series that actually have this behavior. So for example, the harmonic series. We compute this ratio for the harmonic series, which we'll do real fast here. You get all excited and say, oh, I got a new test. I'm going to test on the hardest series to say anything about. The limit. Let's look at the sum from n equals 1 to infinity of 1 over n. So we're going to look at the limit as n goes to infinity of an plus 1. Here it very much matters which one is on top. An plus 1 must be in the numerator. Okay. Actually, in this particular case, it doesn't matter, but generally it does matter which one is on top. This is equal to the limit as n goes to infinity of n over n plus 1, which is 1. So what can we conclude? Nothing. Ratio test doesn't work. In fact, suppose you put n to the p right there for any p series. What's the ratio test going to say? I have no idea what's happening. So the ratio test doesn't work on p series. This is why we break them out and treat them separately. So, no conclusion. No conclusion from the p series. We know this diverges by other means, right? All right. So now let's break it out to work on some gnarlier questions. Maybe you hate constructing inequalities. You hate constructing inequalities so much that you'd prefer never to think about inequalities involving factorials. And somebody comes along and says, I think that this series fails to converge, but you hate inequalities. You don't want to compare that to anything, right? It's unclear how to build a comparison. You don't even know. I don't know, n factorial, bigger, smaller than exponential. I know nothing about orders of growth. What's the most powerful tool you've got available to you? Well, the ratio test. So let's just try the ratio test. In the background, if you want to put this in your list of tools, the reason that you might think ratio test is specifically because there are factorials in the question. So what the ratio test says is, okay, that's the limit, then goes to infinity of an plus 1 over an in absolute value. Everything's positive here. That's okay. Limit as n goes to infinity of 1 over n plus 1 factorial over 1 over n factorial. And I chose this problem specifically so that I could remind you guys how factorial arithmetic works if you haven't done it in a while. This is equal to the limit as n goes to infinity of n factorial over n plus 1 factorial. If you haven't thought about the way that factorials cancel in a while, or you've never seen this before, one way to figure out what's going on in a problem where you have quotients of factorials is just to expand them out. Remember that a factorial just says start multiplying numbers at 1 and keep going until you get to the last number in the list, which is n. Like if this was 10, then it would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the bottom, we have the same list, but now we're ending at n plus 1. Once you've got it all expanded out, it's often easier to see what's going to happen when you start canceling things, right? One, I guess there's no reason to cancel the ones. The 2's cancel, the 3's cancel, the 4's cancel, the 5's, the n minus 2's, the n minus 1's, the n's. All that's left over is this lonely n plus 1. Survived the great cancellation. That limit is 0. Now, one of the complicated things about keeping all these tests straight is that this is at least the third theorem that we've looked at that has a condition on some limit. Sometimes things are not allowed to be 0. Sometimes they are. In the ratio test, a limit of a series being 0 is an information giving piece. It gives you information. What does it say? The only condition on this limit is it's less than 1. That's the only condition. This is less than 1. So this sum is, I guess we can say absolutely here because all the terms are positive, but absolutely convergent. Even better, the fact that we did this in the ratio test and we know this is absolutely convergent means we automatically know that if we saw this, this would be absolutely convergent. This would be convergent as well in the same way. Okay. This is like typical of these ratio test type constructions. I'm going to do a couple more examples of the ratio test at work. Okay, so here's kind of a gnarly one. Does Stuart do The grossest problem. Oh, that's pretty good. Okay, pretend you had this calculus book and you're reading it on your own without ever having been told by your professor that you can always figure out what a series does. Not always, but often by looking at orders of growth. What does the orders of growth say about what should happen to the absolute values of this series? Converge or diverge? Why?
Just 3 to the n goes faster.
Yeah, that's a polynomial up here. On the bottom we have an exponential. And exponentials go faster than polynomials, so this is going to go fast enough. That's the intuition you should have. So I suspect this is going to converge. You don't need, but the thing is, you don't need to know any of that, because as soon as you see a structure like this and it's alternating, and you don't want to use a comparison test, you can just do it all at one go with the ratio test. And all you need to be careful of is making sure you construct the terms correctly. Limit as n goes to infinity of the absolute value of an plus 1 over an. Basically, the only way this goes wrong is when people don't construct this limit correctly. Okay, so the minus ones are gone because they don't leave minus ones in the limit after you pick absolute values. Very common error. Okay? The whole point of the absolute values is to kill that. An plus 1 is this formula with n plus 1s plugged in for all the n's. And so we get n plus 1 to the third over 3 to the n plus 1. On bottom, we have n to the third over 3 to the n. So really this is an exercise in your ability to handle calculus 1 limits and the algebra of pre-calculus. Continuing. 3 to the n over n to the third times n plus 1 to the third over 3 to the n plus 1. Okay. How does that simplify? An obvious move I can make here.
3 to the n.
Sure. N to infinity. I'll make that into a 1/3. Now, suppose I already told you guys that since I was being nice to you and I trust you as mathematical or as mature mathematical students, big kid calculus students, that if you see what a limit is and it should be obvious, you can just tell me what the limit is. What's that limit? What is the limit? I mean, the 1/3 is not doing anything, right? What does this do? When you multiply the top out in your head before you get started, what will the leading term be when you do that? N cubed, right? If you actually expanded this, what I'm saying is if you don't see it, make sure you expand it. If you do see it, it's okay just to write that this is like n to the third will be the lead term here. It will be. So it's n to the third on top and n to the third on bottom, which means this whole limit is 1/3. Now, if you can't do that in your head, do the expansion. You never have to do the algebra. It's just about discovering what the lead term happens to be. Okay. This thing is on the order of 1/3 times n to the third over n to the third. Because this is n cubed plus 3n squared plus 3n plus 1. What do you conclude? Less than 1, absolutely convergent. Make sense? Okay, ratio test, incredibly powerful, does require you to think somewhat about what's going on with these algebra things, because you get these these fractional sort of expressions that need to be simplified to compute the limit. So there's a little bit of work associated with computing just to get to the point where the limit can be taken. But you can see it interacts really well with these geometric type things, right? These exponential type structures just cancel really cleanly. And these polynomial type expressions turn into limits you can compute directly. And the factorials we saw already also cancel very well. Okay, so the ratio test is probably the single most important test for convergence. But I have another test to give you, which in applications turns out to be even more important. It's called the root test. The root test says, one, if the limit goes to infinity of the nth root of an is equal to L, which is less than 1. And the series, convert series of n converges absolutely. So this is a different way of measuring the growth of the terms of a series, right? Instead of looking at the ratio of a series to itself, here, I don't even need that. I just take the nth root of the nth term. If that turns out to be shrinking, then the series goes to zero, the sequence goes to 0 fast enough to make the terms out. Now, this should scream out to you that this is going to be really awesome when there's just a bunch of nth powers running around inside of a series, because nth roots of nth powers destroy each other. So this works on things that have lots of powers running around, but not factorials. You wouldn't want to do a factorial like this. 2, the limit goes to infinity of the nth root of a. Actually, this time I'll point out that this is often written like this. Is equal to L, which is bigger than 1, or infinity, and the sum of the AN's diverges. And you might think, aha, maybe this gives me an advantage over the ratio test. It turns out that the same flaw exists. The limit as n goes to infinity of AN to 1 over n is equal to 1, inconclusive. Okay, so why would you do this? You think? We already know how to deal with nth powers. They're all geometric series. Except sometimes the root test lets you get into the core of things that look like this. So mixtures of things. So you can make an argument in a series like this. You can make the argument that, I'm sorry, I missed absolute values all over this. You don't want to be taking square roots of negative things, right? So there's supposed to be absolute values everywhere I've applied the root test. I apologize. Don't take square roots of negative numbers. We're not in complex linear. All right, so why would you think ratio instead of root here? Or root instead of ratio? If you set this up as a ratio test, you can imagine there's going to be an n+1 right here, which means there'll be an extra copy of whatever you made. And also there's going to be n+1s all over it, and nothing is going to simplify algebraically. There'll be no cancellation. So if you did this with the ratio test, you just get this mess of algebra. Instead, you might think, well, look at that. There's just this to the nth power floating around out there. And fortunately, I have a test that gets rid of those. So you go, I'm going to use the root test. Because you just thought for a minute about 2n+1 + 3 over 3n+1 + 5 all to the n+1 divided by 2n + 3, 3n + 5 to the n. Ugh. whole ratio. That's really what your thought process should be, right? Like, oh my God, no, I don't want to. Okay, so you get this with the root test. The limit then goes to infinity. Looks trivial until you're looking at an exam and you have to choose the right method, right? That's really where the difficulty comes from. 2n plus 3 over 3n plus 5 to the n to the 1 over n. It's like somebody wrote a textbook and picked this out as an example because of how easy it is to compute. N to the 1 over n, powers multiply when they're raised to each other. So this just becomes the limit. Then goes to infinity. 2n plus 3 over 3n plus 5. Which is 2/3, which is less than 1. So the whole point of the root test is that it annihilates exponents. So if you have a series with terms that you can write as something with an exponential, you can often do this. So this is absolutely convergent. Okay, so basically, sum up now. Sum up all of the tests that we have available. So this completes our set of tests for convergence of numbers. Okay, we're going to be talking next about writing functions as series. That's what Taylor series and power series is about. But now we've completed our set of tools. We're going to do some more examples next time because I'm almost out of time here. But basically now we have our complete tool set for testing convergence. What is the first thing you should always test before you test anything else? Always. Test for divergence. Do the terms go not to 0? Interesting logic in that construction, but test for divergence. So basically, if the ands don't go to 0, divergent. Always test 1. What else do we have? Geometric series. Telescoping series. Those are just forms. The integral test, which relates convergence to improper integrals. Right? Comparison test. Limit comparison test. Ratio test. And root test. That's a lot of tests. Oh, I missed one. Alternating series test. The challenge of this class has a reputation for being very difficult. The challenge of the class does not necessarily come from applying each of these tests. The challenge comes from having a pile of series and having your professor say, do all of these converge or diverge? And you have to go through this huge list of techniques and identify which one goes with which series. Sometimes only one will work. Sometimes many of them will work. But the idea is you have to practice these enough so that you can pick out the method. And that's what the focus of the next couple of lessons is going to be. We're going to do some more examples of the ratio and the root test, but our real focus is going to be on how you choose which method to use when you're looking at one of these series. Okay. And what I'm going to do is in the background, I'll just post, I'm going to post a huge list of problems. You don't have to do them all. You can just, the goal will be if I put 100 series up in some PDF file, to be able to go through and say which test would you use on each one. Okay, so repetition is going to help with the pattern recognition, and that's going to make the exams easier to do when we get there. All right, thanks for your patience, your attention, and I guess I'll see you guys on Thursday, because it's Tuesday. All right, that's it. Bye, guys.